This video is on colligative properties. We're going to talk about three of them: vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. And then I'll make another video on how to do calculations with them. So what I have here, we're talking about vapor pressure lowering, is three different views of the same beaker as best I can draw. And in this number one position, I just have a solvent, water only, no solute or anything else in there. And we know that what happens in here is you start to develop a vapor pressure because you have liquid leaving and gas entering the solution, gas condensing, liquid vaporizing in a dynamic equilibrium. And we develop this vapor pressure here in valve number 2. Well, in valve number 3, what I have is in the red dots, I have a solute, for example, sugar and water. So sugar would be my solute. And these sugar molecules, and if I blow this up a little bit, if I look at a little piece of that, the sugar molecules then attract the water. There's attraction forces between the sugar and the water. And that tightens the hold on these water molecules around here. If you tighten the hold, if you're holding them harder, it becomes harder to vaporize. And one way to think about it is the amount of vaporization decreases, but the amount of condensation stays the same. And so the vapor pressure drops a little bit, which I've indicated here. On this side, I have a smaller vapor pressure over here than I do on this side. That's probably the best way to think about it. There are other ways. Now, this has a direct effect on the boiling temperature, because if you remember, the boiling point is the point at which the P vapor is equal to 1 atmosphere. So if 1 atmosphere is here on my graph, and I lower the vapor pressure, remember what that looks like. It'll start down. If this is vapor pressure, and the black line is water, here's what the vapor pressure will look like. I got my 1 atmosphere in the wrong place. I'm sorry. This is 1 atmosphere up here. And this is the boiling temperature, 100 degrees. But now it has increased over here to maybe 102. We don't know. We just know it goes up because the vapor pressure goes down. This is called boiling point elevation. All right. The third one is freezing point depression. So in freezing point depression, here I have my solution again, and here is my sugar molecule. And we have the same strong interaction between the solute and the solvent. And that interaction prevents, you can think about it this way, prevents the solution from organizing, because I have the water molecules like this surrounding my solute, perhaps, they cannot organize into nice crystalline structures. Okay, this is my ice forming. Because to form a crystalline structure, you have to line up perfectly. So if I have these solute molecules in here, they're going to stop it. They're going to prevent it from doing that. So I have to lower the temperature even more to get them to organize into a crystal structure. And this is completely dependent upon the number of species you have in there, not the identity. It's never important on the identity. So if I have 1 molar sugar solution, that gives me 1 mole of particles, molecules, per 1 liter of solution. But if I have 1 molar calcium chloride, which is what they do use to melt ice, I get 1 mole of calcium and 2 moles of chloride. Remember what this is. It's a calcium plus 2 ion and 2 chloride minus 1 ions. And so the total number of moles of ions I get over here are 3 moles of ions, and it doesn't matter what the identity is. It only matters how many moles of things that you get, and 3 moles is way greater than 1 mole. So we expect 1 molar calcium chloride to lower the freezing point more than 1 molar sugar. And that's exactly what happens. That's why they use calcium chloride to melt snow. It just lowers or melt ice. It lowers the freezing point. 1 more, osmotic pressure. So this is kind of going to be the same. So here I have osmotic pressure, and I have water on this side and water on both sides of this drawing. And you would expect that the water would be the same height. You've experienced this. These heights should be equal. Well, what happens when I throw solute on this side? And notice I have a little dashed line. That's called a semi-permeable membrane. So I'm going to throw solid on this line, and here's my dashed line. Okay, and that semi-permeable membrane will not let the solute cannot go through. It's like a filter paper, like coffee filter paper. The solute can't go through, the coffee can't go through, but the water can. And so it's going to want to help dissolve these molecules, and so what happens is water moves in that direction, and we end up with this situation on the right. And we get a difference in height because the water moved that direction. Okay, here's my membrane. And this height difference is called the osmotic pressure. And again, it's only dependent upon the number of things, solutes that you have in there. So ionic compounds are way more effective than molecular compounds. Okay? And that's osmotic pressure. And that's really all you need to know about them. Remember that it's going to be dependent upon the number of ions. And so this has a particular term, that number of ions. It's called the Van 't Hoff factor. And it's given a symbol I, and I equal the number of ions formed, or the number of moles of ions, the number of formula units of ions. So for sugar, sugar is not ionic, it's C6H12O6. The Van 't Hoff factor equal 1. For any molecule, it's equal to 1. But for any ionic compound, for sodium chloride, I have 1 sodium ion, 1 chloride ion, and so the Van 't Hoff would be equal to 2. That's an I. Let's do calcium bromide. For calcium bromide, I would equal 3. I have 1 calcium ion, a calcium plus 2, and 2 bromide ions. So there's 2 Br minuses, and that would be the Van 't Hoff factor on this. And that determines how effective something is. We'll go to the next video to explain how this works and do calculations.